All right, so let's take another shot at this compressed natural gas problem. It's a good one. So first, there's this whole concept called the heat rate, and in some ways it's just the opposite of an efficiency, because let me show you what I mean by that. It's the BTUs that are going in. It's the BTUs of natural gas going into the system to spin a turbine to make electricity. So it's the electricity that's coming out. And I think I put a little, yeah. So what you've got is two separate streams coming into a system. You've got air that's been compressed. So here's one sort of chamber, and then you've got natural gas, which is also compressed. Those two are mixed together just like in any turbine, whether, jet turbine, natural gas-fired turbine, steam turbine, etc. Spins your turbine, makes electricity, kilowatts come out, or kilowatt hours come out. Way to think about this chamber is that you're going to charge it up to, well, I wrote 75 psi. It's actually 75 bars. And when it's essentially discharged, or as low as you're going to let it get, it's going to get down to 50 bars. And the way to think about this is at 75 bars, you're going to get, well, better way to think of it, it's going to take 4,500 BTUs to get a kilowatt hour out. Now down at 50 bars, or low pressure, it's going to take 8,000 BTUs to get a kilowatt hour out. So you're going to need, at low pressure, you're going to need, so what's a good way to write that? So at low pressure, you're going to need high natural gas or BTUs. At, I kind of ran out of room here, but at high pressure, I'll just sneak it in here. At high pressure, you're going to need lower BTUs going in. Hopefully that makes sense. All right. Now, let's go in and...
Is that because there's more air going into it's under more pressure?
It's under more pressure, so it's coming out quicker. I mean, you're not going to mess with your combustion, because you're still going to need the same stoichiometry. You're going to still need as many air molecules per natural gas molecule. It's just, it's going to come out faster because it's higher. Yeah, right. Okay, and I think, all right, so here's what we did. Well, it's, let's do our function first. Oh, here we go. Okay. So what we're looking at is heat rate as a function of pressure. So heat rate as function of pressure. Now we already know that at low pressure, so down here at 50 bars, we're going to have to have a relatively higher heat rate. And at 75 bars, we're going to have a relatively lower heat rate. So the slope, we know right off the bat, is going to be negative. So we just set up the equation, and this is essentially y equals mx plus b. Heat rate equals m, that's the slope. P takes the place of x as pressure, plus whatever the initial heat rate is. We're never gonna hit that. I mean, we're never actually gonna go down to zero pressure, but we're still gonna need it to find our equation. So, to find the slope of that line, we just write, we just start out with slope equals m equals, hey, what's up, Jesse? Equals rise over run. And when you do your rise over run, you start from the right and you move back to the left. So the rise, in this case, starting from the right, with 4,500, the heat rate of 4,500 minus the left value, 8,000. And again, you have to match these numbers up. So where you saw the 4,500 on top, you got 75 on the bottom. So minus, or divided by 75 minus 50. So 4,500 minus 8,000. Let's do that little bit of math here. 4,500 minus 8,000 equals negative 3,500. 75 minus 50 is 25, so divided by 25 equals negative 140. We knew the slope was going to be negative. It is. The units on that are just HR divided by bar. That's the, so HR divided by bar. So dump that back in to find. So what we're looking for is the value of B, or somewhere up here is our B, or in this case I'm just going to call it HR naught, the initial heat rate. So you can just plug in known values. We know 8,000. We know our slope. We know at 8,000, right here, that we're at 50 bar. This is what we're looking for. Just becomes plug and chug, and the initial HR is 15,000 BTUs per kilowatt hour. So how's that? So the final equation for heat rate as a function of pressure is heat rate equals negative 140 times pressure in bars plus 15,000. So now, and this is kind of the same deal that we've done in our pump storage. Figure it out analytically first. What we have right here is an analytical model, and now we're going to go into our numerical model. Okay, so here's our high pressure at 75, and all I did to get this, I just typed in 75, and then right here I just said equals that minus 1. Take that guy, drag it down until you hit 50. All right, and now this number is, well, it's the function, so let's take a look at the function. The function is $3, so that's my slope. So that blue box is my slope. That's my M. We already calculated M, negative 140, times D5, that's X. That's our MX, and X is just our pressure, plus B, or plus H naught, 15,000. Take that guy, drag it down, and the numbers magically appear. And you can see what I've done. I used the absolute reference, those dollar signs. so that that slope and that B naught stay the same.
I
Okay.
got it figured out.
Okay, all right, good, thanks. I heard some big sighs over there. I'm glad there were good ones.
I was limiting my outcomes.
Okay, so let's go back into the problem and see how far we've gotten. Okay, so here's our next little conundrum, and I got to say this is something we're going to have to kick out to the forum because it's I think there's a parabolic function lurking in here somewhere, but I can't quite find it. I could be wrong, but I think somehow it ends up that as that pressure drops, the amount of time spent at each pressure decreases. So as you get to the bottom, it's almost like think of a balloon decompressing. Like initially you kind of, and then right at the end, whoop, there it goes. Something like that. And that's what this is. It's a big balloon underground. Feel better?
Don't try and put the 100 feet in until you get this.
Yeah, okay. Yeah, I think you ended up what we did.
It goes at the end.
Okay, super. Okay, good. We're on the same page with that.
So it goes down like.
Okay, so what we're looking to do is make power at a rate of 50 megawatts. And so I put this guy in at 50,000 kilowatts. That's the power we're trying to make out of this. So now we have to pump in enough air and enough natural gas to make 50 megawatts, or 50,000 kilowatts. So what I came up here, with, and I don't see anything too wrong with what I've done so far. And this is kind of maybe a little confusion for you, but 3412, this is a good exercise in units. 3412, what is 3412? Well, I've got it written in here as BTUs per hour per kilowatt. Now, you probably haven't seen that formulation before, but let's go and figure out where that 3412 comes from. So if I just come out here and say BTU per kilowatt hour, there it is, 3412 BTUs per kilowatt hour. What are
bioenergy.
What's that?
If you haven't seen it yet, you'll see that.
Yeah.
Bioenergy.
Yeah, there you go. So what does BTU measure? Sure, and heat is energy, yeah. So it measures thermal energy, kilowatt hour, also energy, measuring electrical energy. Now, BTUs per hour, what's that? Power, thermal power. Kilowatts is also thermal power.
How
So,
do you get the BTUs per hour? Sorry, Wayne.
oh,
What's the equation you use for that?
well, this guy right here, you mean? Okay, so first I converted the energy conversion, 3412 BTUs per kilowatt hour, into a power conversion, 3412 BTUs per hour per kilowatt. So I just divided both of them by 1 hour. I mean, there's really no magic to it. I mean, just imagine, well, it's tough to visualize what a kilowatt hour of electricity is. I can imagine what a BTU of natural gas is. What is it?
Well, every time you drink
BTU.
a Corona is 0.2 kilowatts.
There we go, okay. But in beer units, it's much easier to visualize.
But that's purely Corona.
Each beverage has its different alcohol
Different
content.
conversion back.
There you go. So, but anyway, what I came up with is, I know that the heat rate changes as a function of pressure, right? And we know that at high pressure, the heat rate's low. At low pressure, the heat rate's high. So, from that, I came in and said, well, I need this many kilowatts. Therefore, I'm going to need this many BTUs per hour. Yeah, what's going on, Mark? So as expected, the BTUs per hour increase as the heat rate increases. And that's as far as I got.
Midterm time, Brett.
All right.
Yeah. Terminal AC circuit stay, kids.
Way to go, guys. Well.